Hello everyone, my name is Dankook from KAIST. Let me talk about LODIC, that is logical distributed counting for scalable file access. Recently, the number of cores and the main memory size are rapidly increased in server. So, the many-core scalability becomes a serious issue in modern OS design. In Linux, the reference counter exists to manage the lifetime of the object. When the thread accesses the object, the reference counter is incremented by 1. And when the access is complete, the reference counter is decreased by 1. If the number of reference counter becomes 0, OS can reclaim the object. In Linux, various kernel objects maintain the reference counter to prohibit them from being reclaimed prematurely while allowing them to be accessed concurrently by the number of processes. But the reference counter has a problem of scalability in many-core system. When many threads try to access the same object, the cache line bounce occurs. As you can see in figure, this cache line contention clashes the performance as the number of access cores increase. To address the problem of scalability, the distributed reference counter is proposed. The distributed reference counter allocates the local counter for each core. Through this, update operation becomes updating the local counter, and the counter query becomes scanning all local counter. However, there are two issues in the pop-core distributed reference counter. First, the memory overhead increase in proportion to the number of CPUs and objects. Second, checking all local counter to reclaim the objects and calculating the global counter increase the query latency. There are 4 existing workers for the pop-core distributed counter. As the pop-core distributed reference counting, SNZI and floppy counter has been proposed to avoid cache line bouncing in the atomic counter. This approach has issues with the memory overhead and query latency for calculating the global state previously mentioned. As the hash table based the reference counting, left cache and paygo has been proposed to mitigate the memory overhead of the pop-core scheme. However, they do not fundamentally solve the limitation of the pop-core distributed reference counter. Still, their memory consumption is proportional to the number of CPUs, and they do not improve the query performance because they have to search the entire pop-core hash tables. Also, when the hash collision happens, they perform in slow path, including the central contention. Let's talk about the design of a LODIC. The kernel object has 3 characteristics. The first is population. There can exist a million counter in many core systems. And second is popularity. The real-world data access is highly skewed toward the small set of the hot objects. The third is accessibility. The access duration is very short, and in the case of the physical page, the reference split is rare. The existing popcore approach has high memory overhead because a local counter is allocated to each core while ignoring the degree of the sharing. On the other hand, the per-process approach can reduce the memory overhead by allocating the local counter only to process accessing the object. The difference between the per-core and per-process approaches is the view on the cost for the counter contention. The per-core approach views the cost of the counter contention as the contention between the processor. However, the process approach views the cost of the counter contention as the between process, considering the degree of the sharing. Because LODIC views the counter contention is caused by the contention among the process, it has the distributed counter with local counter are defined in per process. LODIC uses the two characteristics about the kernel object. Using the popularity characteristic, we define the counter with respect to the degree of sharing. And considering the access brevity characteristic, we did not consider reference split. Also, we focus on the scalability of the access to the shared pi block among various kernel objectives. Because the physical page has a large population and the pi block has high degree of the sharing compared to the anonymous page. And the access duration is so short that the reference split rarely occurs. LODIC has three objectives. By designing the number of counter as proportional to the degree of sharing, we will have high scalability for shared pi block access and low memory overhead and correlations. Three key techniques are used in LODIC implementation: file mapping, reverse mapping, and counter embedding. The first problem with the LODIC implementation is how to allocate a counter for the physical page as the process. We solved this through the file mapping. The process address space is implemented as the set of the VMAs. When the process maps the physical page, the VMA for physical page is created. Therefore, we allocate the local counter to the VMA for the map the page. The second problem with the LODIC implementation is how to quickly find the map the VMA from the physical page above the shared pi block. We solved this through the reverse mapping. The existing Linux use the file space-based reverse mapping for page reclamation. When the pi block is mapped by the multiple process, the existing reverse mapping maintains the VMAs for the mapped physical page of the all process in the red-black tree. However, unlike the page reclamation, where the reverse mapping is not in the critical path, the existing reverse mapping does not meet the required level of the performance and scalability for LODIC. Because searching all VMAs in the red-black tree of existing reference mapping to find the mapped VMA of the specific process may cause the performance degradation. So we propose the process space-based reverse mapping. Since the page cache access is executed in the user space process context, LODIC can directly exploit the red-black tree of the process space data structure. Due to the mapping mechanism in Linux, the mapped VMAs is likely to be located just below the stack. LODIC reverse scan the VMA list of the process space starting from the mmap base that close the stack. Using the process space-based reverse mapping, LODIC accelerated the VMA search. The last key technique is counter embedding. To lower the memory overhead, we use the unused bit in the page table entry. LODIC in 64-bit x86 architecture is using the 7-bit for embedded local counter. This is all-in-one view about the LODIC. When reference occurs, we first look up the physical page plane. If the page plane is mapped, we use process-based reverse mapping to find the mapped VMA in the process. After then, we obtain the virtual address through the found VMA. And we increase the local counter defined in the page table entry from found the virtual address space. This is the evaluation part. We measure the throughput on the shared pi block read using the DRBH workload on FX mark. The performance of the LODIC using the process space-based reverse mapping is increased by 65 times against vanilla Linux under the 120 CPU cores. We also measure the web server throughput. We used 50 NGINX reverse process server and 50 WRK client process that make the read request for the same pi. The performance of LODIC is increased by 2.5 times against the vanilla Linux under 50 client process. Lastly, we measure the counter query latency. For 1 gigapi, 3 LODICs with different ratio of the mapped pi block were measured. For about 10% mapped pi block, LODIC show less than 1/4 query latency against the backward distributed counter. This is conclusion. LODIC take a process-centric view in designing the distributed counter scheme. That is the view as the counter contention is caused by the contention among the process, not by the contention on the processor. From this point of view, we allocate the number of the local count with respect to the actual degree of sharing and can reduce the memory pressure to almost none. As the result, LODIC increases throughput on the shared block read by 65 times and web server performance by 2.5 times against the vanilla Linux. And the memory pressure decreases by 13 times against the backward distributed Laplace counter. Thank you for listening to my presentation.